Hello, ma'am. Good morning. Can we start now?
Good morning, sir. Uh,
Yeah, good morning, ma'am.
yes, sir. Yes, sir. We can start. I will just introduce you.
Yeah, yeah, so I'm already introduced, so I think
Acha,
we can start
okay.
it.
So, welcome back to the third session of today, and it is on convolutional neural networks, which will be taken by Professor Rajesh Kumar. He had already introduced this course on the first day, so I request him to start the session.
Thank you, Dr. Priyanka, and good morning to all of you. Probably good noon at your side. This discussion is on convolution neural network. We'll try to see whole structure, why convolutional neural networks, and then what are the different operators people which we can use, and then what are the developments in this area, and then if time permits, we will take one case study here. Okay, so let me take a point, and then we can, yeah. So more nowadays we are using a lot of images, basically maybe health images. So you can have x-rays or MRIs or scans, some kind of a scan, maybe scans of your chest or brain or bone or something like that. And then what we are looking for, we are looking that a machine can automatically uh, find out the issues in those images and can give us some kind of recommendations. So there is a strong application of this area, CNN, in image diagnosis and identification. So I'm just taking few slides to motivate ourselves why CNN and what are the applications where now this CNN and models connected to CNN, they are being used. So healthcare is full of it, and you can see in healthcare many applications CNN people are using. They are using at the signal level. So signals can be your heart rate, or it can be your brain signals, or it can be your muscle signals, and then try to figure it out what are the issues and how is the health of a person. They are using CNN on the, I told you, on the images, X-ray, or maybe X-ray images, or scans, CT scans, or even image of a person as it is, face and all those things. Try to figure out various complexities and the condition monitoring of your human being. They are also implementing on the DNA level, and working patterns, and the applications are enormous. So you'll find healthcare is a very popular area where CNN and some combination of CNN or hybridized CNN models are being used in a very big way. Self-driving car is another very good example, where you can see the automation structure of the vehicle where there's no driver, and you can see a lot of things are there. The vehicle is identifying the obstacles, checking its speed, making a decision, going right and left, and then identifying the location, moving from one point to another point, and everything is automated there. So that is another interesting example of the approach there. I told you this is one case in healthcare, medical disease identification. Whether there is a disease or not, if it is there, then how much is the impact? Not only if there is a disease or not, if there is a tumor or no tumor, but what is the size of a tumor? What is the, now if you see recent articles, what is the grade of the tumor, and the things they are identifying much more in depth about these images and all these things. These are being done automatically by the machines, and the machines they are using uh, they are using other methods also, but CNN is one of the popular method which is being used there. Voice recognition nowadays it is very common, but again, voice we have, that is a signal, and then signal is basically uh, processed, and then you can convert it to 1D CNN models are there, which can be used to recognize uh, what person want to say. That is one part. The second part is the mood, behavior, health status from the voice signal, and that sounds interesting. and that is the area where people are working and using these approaches there. Auto texting, and there are various auto texting is there. So we have document, and then you can see document extraction of the meaningful out of it. Now these you will find some kind of a lot of uh, GPTs are used. So lot of AI tools are there where you pass the text, and then text is summarized, or text is highlighted, what is plagiarized, and all those things there. There also we can use this approach. Finance is full of it. Prediction models, people are using it uh, to get the predictions as accurate as possible. Sentiment analysis is full of it. You have an image, and then you can find the sentiments from there, whether person is happy or in anger or in sad. The machine is identifying those things automatically. Auto coloring, nowadays you can see a lot of things are available here. You take black and white stuff there, and then you can do automated coloring of it and make the things beautiful. Text conversions, so they are setups where you have text in one language and you want to convert it into another language. So it's not purely CNN, but yeah, CNN is, you can use it and then hybridize it with another kind of approaches there. Other approaches, these are the earthquake estimations, the movement of earthquake, the impact of earthquake. Those studies are being reported in the literature. This area is full of it, and that is the digital marketing. And you'll see that this is being used in a very big way. So you are using social media, you're and using some YouTube and other things there. So at which instant, what should be the duration of the advertisement, the design of the advertisement, and everything. You'll find a lot of studies and a lot of combinations of these technologies being used there. Architecture design is full of it. You can see here, this is one of the case study that the image of the structure or the uh, or the city plan is passed, building plan is passed to the model, and model estimate about that, like what is the appropriate positioning of solar panel, so that we can say how much of energy and all those things there. Product design is full of it. So you give an input, and then based upon your design, or based upon the consumer preferences, and what the consumer searched or what consumer purchased, it will automatically do the coloring and design the product for a consumer. So it's the customized designing of the things there. Uh, it brings a lot of transformation in engineering. So like here you can see there is a this one picture is a transformer blades, and we know that if we use the transformer in electrical engineering, so it will dissipate heat through these blades, and that earlier people used to place sensors here, so that we can check it how much is the temperature, and if the temperature is beyond certain limit, then we can take an action to do some do some corrections, or we can make it off. uh, but it's critical in many cases. What people are doing is now they are taking images, thermal camera images, and from images uh, they try to predict it, that what is the temperature at particular point. Why sensors limitations are there? Take this case. This is a case of a motor, and you can say this one is inside the motor, that there are windings which are rotating. So what is the temperature at a winding? So these are the images taken from the thermal cameras. So putting a sensor inside a motor, and which is rotatory at a very high speed, create a problem, and put a question on the durability and all those things. But from the images, we train the models and find out what is the temperature, and if the temperature exceeds, that means there is some problem in certain winding, and we can stop that machine and then repair it before it get totally damaged or it create a big problem. So these models, these approaches bring a major change there. And that is what is the point here, that how it is being done there. Okay, robotic operations is now getting popular every day. You'll find in most of the hospitals robots are there, and they assist the doctors to perform the operations and all that. City planning we have already discussed. Some cases, uh, this one is basically vehicle speed detection. So now although you can see that there are on the roads the traffic people, they are standing. Sometimes they are standing with speed guns, but most of the time it is automatically done. So the camera, and from the camera the images, and then frame rate, uh, and from the frame rate and the images they can easily predict what is the speed of a vehicle, not only for one to one but many vehicle at a time. And then they can put an alarm who is violating the speed limits and all that. So that's another practical example which is available there. Okay, so there are a lot and lot of such examples you will find. These are particularly electrical vehicle examples, which I'm putting it here. So I'm moving forward, just to check it, just to understand now what is CNN, how it works, and other models. So our agenda is today is how a computer read an image, because that's the beginning point from where we can build the whole system. And then why we are not going for a fully connected networks, what are convolution networks, okay, and how they work. And then some applications we have already seen, but a case study we can discuss at the end. So now this is an image, this is how we see the image. But when we pass this image to a computer, then computer will break it to three channels, basically RGB channels. And then and then that those channels, when we talk about, those have basically, you can say, uh, configuration. So the size of image is basically, you have breadth of image, okay, and the length of image, and then there are pixel values. So when you pass an image, it can be taken to three channels, and then each channel will be read like this. So there are some values, some numbers there. Okay, so when you pass it, so this image, this is what computer can uh, take it, and this is one channel, and likewise we have three channels, which when we combine it, form like this. So now if I pass an image to my computer, a mathematical model, we have numbers, and now the rest of the part is our mathematical operations. How to perform mathematical operations to get a meaningful numbers from these numbers there. So so that is now the next target. Okay, and what is the issue there? What is the issue? So issue is, okay, if I take these numbers, okay, and then arrange them in a sequence, and then I develop a neural network over it, then I can do probably do I can do the classification, whether this is a dog or a cat or something else. But there is a problem, and what is the problem? Just check it here. If I take an image which is basically MNIST data, which is a very simple image, you can see the pixel size, 28 cross 28 cross 3. This is the pixel, and I develop a fully connected network. Okay, I'm using a deep network, fully connected one. So the number of the weights in the first hidden layer, okay, here only, that will be 2352. And if you use many such layers, you can think of how many weights are there, which we need to train. Well, in practical cases, and more complex, not practical, more complex cases, our image, if my image size is 200 cross 200 cross 3, that those are pixel values. Then the number of the weights in the first hidden layer will be, you can see here, 120,000. And now you think of how many layers you are using, and that is the number I have to train. And now you understand, you already gone through neural networks, how the propagation takes place. So how many weights? For each weight, we have a kind of equation and the calculation. So that becomes very bulky, and that's why you'll find that we need we need very high computing systems or something like that, or we must have a huge time to train it. Otherwise, it will not get trained. So if this is the scenario, we have only two solutions. One, I go for high computational resources. If I'm going for this setup which we have discussed, so we have to go for GPUs and all those things which are costly. Also, it will end up with the overfitting kind of thing sometimes because of the training and overtraining, because of the weights. Weights have interdependencies, so many weights, and that will end up with kind of a overfitting kind of structure there. So now we are looking for a thing where we can reduce the overfitting, and whether it will help us in reduction the cost also. Well, from here, some hypotheses appear from the medical side, and we'll go to that. But the good part here is, can we make this fully connected network a sparse network? That all the layers, they are not connected. You can see here, this is connected here only, it's not connected to other neurons. So if I go for this kind of a sparsity, it's not fully connected, then one thing is very clear, that overfitting will not be there. And the second thing is, the number of connection reduces, and that's basically reduction in the number of the weights. Okay, so if number of weights reduce, then I can process it with the low computing machines. That's all our problem, but the thing is, challenge is how we do it, or how we cut these things, because we must have certain kind of a mechanism to to take a decision whether it should be connected, with this neuron or this neuron, or it should not be connected. And then what is actually happening in our brain system also. So people come out with some theories, some studies, and try to figure it out. And this is how our visual cortex also works. So visual cortex means how we see the things. So we have a picture, and then from image, neurons are excited and they create a certain kind of impression in the brain. We recognize it, and it is observed that our brain also never stores the whole image as it is. It stores the image in parts, and then it combines to recognize the things. Well, that is something very exciting, and that will help us in building a kind of a new algorithm. So let's take two things from here. One, we don't need a fully connected whole of the network to make the things easy. And the second thing is, uh, can we take the things in terms of small segments, and then we combine those to recognize these things. Well, that helps in building this algorithm, and that is what we are going to look for here. So in convolutional neural network, there are four layers basically. One is convolution layer. We'll go one by one. Value layer, pooling layer, and the end at the end we will go for a fully connected layer. Okay. Objective job is, if some pattern is given, we are looking for a thing that specifically can my machine or model can recognize it. Once my model is able to recognize, then I can do a lot of things. I can do classifications and rest of the things there. Well, you can check out on the check out or you can defend it that, like, okay, we have this image and I want to recognize this image. So I store this image as it is and then compare box by box, and depending upon how much is the comparison, I can easily make a decision that this is X. Okay, you can do it. But now the child, you can see here, I have taken only the 4 samples. This is also X, this is also X, this is also X, this is also X. And there are other ways of writing X also. Which image you will store? And then how you map those things? How you check it that pixel by pixel. and it becomes a complex. This is a simple problem, but still it has a lot of complexity. Okay, but that is one way of thinking, and that thinking will help us. Okay, so let's build the concept over it, how we can do it. So say I want to analyze this signal. Okay, this is basically, you can say, your cardiac cycle. Here is the amplitude. You have one cardiac cycle to this point to this point, and then you have another cardiac cycle, and it's repeated. I want to analyze it. So one way is, okay, I'll take all these points, and then what you can do is, I can extract a features in a different way, and then many features, or I take a point by point, every point what is the value, and store it. Okay, so you can say this is a time. So every time I break into this time zone into very small segment, and then what is the value at amplitude, and then what is at this value, what is the amplitude, at this value, what is the amplitude, and how much is this time, and then I compare it with the bench one. It is problematic, but what we can do is, let's take this whole 2 cycles here. Okay, from here to here one, and another to here one, and I'll hit some important points. Okay, so this one is one important point, this one is one important point, this one is an important point, this is another point. So at every point I'll take one value. So instead of taking all these points here, I'm just taking few values here, x1 to x8, but still I can see that this is also still big. So then what I'll do is, these are the, let's take the only, I'm taking 8 features, 8 values, and then what I'll do is, I'll take these 8 features, and I'll take a fully connected neural network which give me output, and I train over it. These are the features I'm taking it. So if my 8 features are this, then my cardiac cycle is good. If there are some changes in these values, cardiac cycle can be bad, and likewise. But still, it's a big. So what we can do is, can we combine these, because we know that x0 and x1. Okay, you can say x0 and x1, they are near to each other, and then x1 and x2, they are near to each other. So if they are near, and so that means they have some kind of a connectivity between them. I can't say that x0, what is x0 and x7, because x7 is a very far away. But I can say that, okay, x0 is the start point, then x1 is the end point. So there is a relation between, you can connect x0 and x1. So what we can do is, we apply an operator over it, and we combine x0 and x1, and then x1 and x2, and likewise. This layer we call it a convolution layer. We'll go mathematically also in the coming slides, and then we take a fully connected. Okay, but okay, so how you do it? You can do it. You can assume that this convolution a non-linear function, or so where, which is basically what we do is, we give some weight to x1, and then give some weight to x0, and then combine that and pass through a non-linear function which will give us y. Okay, so it's a simple operation there. Okay, but by doing so, what is happening? The feature, earlier there are 8 features, now there are 7 features. Okay, so we have done some operation over it. That's a convolution operation. Okay, you can have a different structure there. You can combine 3 to 1. So then if you do that, then in that case, 1, 2, 3, 4, 5, there are 7 there, and then you can have fully connected lateral network over it. Then what you can, another way is, you can apply a convolution layer, and then again you can apply another convolution layer. This will help us in reducing the things there. Okay, but at the same time, it will help something more important also. We'll discuss in the coming slide. And then I apply a certain operator there, and the operator I use it like, okay, whatever is the maximum value between these two, I'll consider that one for further calculation. So So this one is basically here we are combining. So x1 is common in both the cases, and then after that we are taking maximum of it, and then again I'm combining. But you can see after 2 or 3 operations, this value reduces from 8 features to 3 features to a fully connected. Now 3 features fully connected network is a small network. You can think of how many weights are there, and the things becomes very simple. Now this you can do it, this is a one dimension, you can do it in the 2 dimension also. So you have both features in the x direction and y direction, you combine them, put a convolution, and you can increase the layers, and finally you will find a network which is a smaller network, fully connected network. This is how this concept is can be taken. So you can see if I use convolution and then max and then again combining them, the network is very easy, very small network which can be trained very easily. Okay, and this is how they have developed it. You will find such kind of figures when you talk about, when you see the articles of on convolution neural networks, how they reduce it and then they combine it. Okay, let's understand it. Let's understand with the example and operations there. So say I want to recognize this figure. Okay, so what I've done is all black I put it 1, and then all white I can put it -1. Okay, just to represent it. So as a human, how we do it? We do it as a human is basically, if this one is the my stored image in my memory, this one is deformed image, I combine them, and then I'll see that how many points where it give me the uh, matching, and based upon that matching we can comment it that whether it is x or not. Okay, okay, so what we are doing, instead of combining this whole, what we are doing is we are making a small segments, and then we try to see that okay, this segment is there where it is. Okay, so it is here. Okay, good. And then this segment is here where it is here. You'll see that is this segment is there. Okay, it is there but shifted, but it is some part is here, and likewise we try to combine the things and try to find out more similarity in the things. This idea comes from, so what we are doing, we are using these blocks basically. We are using these blocks of different size, and we are matching it. Well, this one is similar like what we thought of, like in our brain, we never take whole image, we take some segments there, and we try to combine those things there. This is how our brain reads. So I'm using this block to see, I'll use this block to see where are the changes, and this block to see where are the changes. Now you can call these as a filters. Okay, so this is a filter. Okay, and I put it over whole of the image and check it out how much is the match, and likewise. Now this is the idea. We check through the filters. Okay, so that is the basically the beginning of the CNN, that is known as the convolution layer. The convolution layer job is it reduces that thing. So what a filter will do? Filter will find out the edges basically. Okay, so like this. What is a filter? Filter is, this is the number. This is a filter. If I make an image, the image will be like this. Now this will be an edge. Okay, this will be edge. And what is the filter? You consider it's like it's a board, and this part, black part, is cut there, and now you move it over image, so it will only give you the output when it will be exactly matching with this one. It's same like as you are wearing a glass. So if you are wearing a red color glass and if you see it, so only when it is red it will give a very high impact, otherwise not. It is same like that's the idea of a filter there. So like if I have this image, this filter, and then I'll move it over this body, and then it will match at certain point. This shape and this shape, they matches, and then we can say yes, this is that part. And then I'll take another kind of a filter, and I take different filters and see where they are matching, and from there I'll recognize the image. That is what is basically it, how it works. So it's extracting of features of the filters. Basically, I'm extracting some kind of feature, that this shape is a feature of this one. And there is another shape which is also a feature. This is what we are doing it here, and how we do it mathematically. Now let's come to the mathematics. So I'll take this filter and move it over here. So how it will match? So if I put it here, whatever the pixel value, what are the values here? I just multiply it. So if it exactly matches, what will happen? The product will be, I think I put it here. So if exactly it matches, what will be the product? So all multiplied, and I take the average, so the value will be 1 if it exactly matches. Otherwise, the value will be always less than 1. Please note it. Okay, so if I take this one, the product, I'll take it and take the average value of whole product. Then if it is 1, then I can say that this filter exactly matches. Else if you put it here, say, it will be not like that one. Okay, so I put the filter here in this zone, it is 1, but so now I'm generating a feature map, and that's what we have discussed earlier also. Now the models, they automatically generate the features, so we are generating a feature map. Okay, but if I put the same filter here, 50% is matching because only this part matches, rest of the part not matches. Around 50% is matching, so the value will be less than 1, it will be 0.55. So if you move it everywhere, this filter, starting from the top till end, you will get these values. Somewhere you will get negative also. So you have done a convolution here, and you can see here this matrix size is 9 cross 9, it reduces to 7 cross 7. So you reduce the size of the matrix also, okay, by using this filter. Okay. So we have 3 filters. If we have decided that okay, these are the 3 filters, what we do is we move these 3 filters whole across it, and then they will generate generate a three matrices, or of 7 cross 7. You can argue here that here this one is only one image of 9 cross 9. Now here it is 7 cross 7, but there are 3 matrices. No problem. We'll see in the future, in the coming slides, what will happen. But these 3 filters, when we are choosing, we have to be sure that they cover whole of the image, and we can see that this this slope will cover all the things in this direction, this slope will cover all the things in this direction, and this one will cover with the overlap part. Well, that's a sufficient enough for us. Okay, so that is the operation, and then comes the next layer. So we denote it like this, and that is basically the convolution operator. Okay, let's move to the next layer, which is ReLU layer, which is basically activation function, because of the non-linearity present there, and we need a activation function. We use a ReLU layer. You can use other layers also, but ReLU has its own advantage. And the advantage we will talk on. What are the advantages? Let's understand what is the ReLU layer. So beyond this point, whatever is the input, that will be the output, but there will be no negative value. We have to avoid negative values, because what is happening here, you can see there are negative values here. If they remain there and we do some operation, they will affect the values on the other sides also. So we use a ReLU function. This is the basic approach, people have used it. So what we operate the ReLU over it, and you'll see all the negative values, they become 0. Okay, so that is the second step which we do. And then the third one, okay, so you can see here it is become, and then comes the pooling layer. Okay, so pool is basically in a small size. Further we are converting into a small size, so we take a meaningful information. How we take it? So we say I've taken this as a filter. Again we have to take a filter kind of thing, or window. You now now filter is not a correct word. Take a window, and I use an operator that out of, in these four, this is the maximum value which is more important. Okay, so I apply a max operator. There are various operators you can use. You can use max, mean, minimum, median, all has values. Now these values are important in a way, like if you have image black and white, if you are using a max, that means you are using the contrast. If you are using min, then in the opposite one. If you are taking a mean of those, you are blurring the images. Those concepts are coming here. So what I'll do, I'll take max of it, I put it here, then move the window, then take max of it, then move the window, take max of it, and that is how I do it. But what will happen by doing so, my size further reduces from 7 cross 7 to 4 cross 4. Okay, so that is how I can do it. So now after, because this one is after convolution, and then I apply ReLU, and after that I apply a pooling layer. You'll see the size is now 5 cross 5, 5 cross 5, and 5 cross 5. Now what I can do is, so this is what we have done so far. Okay, uh, uh, or 5 cross 5 or 4 cross 4, sorry, 4 cross 4, depending upon the filter size and all those things. So you have input image, you use convolution, you use ReLU, and then go for pooling, and you have three images, three matrices basically of 4 cross 4. But still, here the size is big. It's a okay 16 and 16 and 16, somewhere the almost same like this one is. But this one is less than this one. Okay, and this one is 1, 2, 3, and this is not 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's a 81 total. If I align them in a line, these are 81, whereas this one is 4 cross 4, so 16 and 16 and 16, so the number is reduced. Well, what we can do is we can repeat it. The convolution, ReLU, pooling, and again another set convolution, ReLU, pooling. Now the size is very simple. It's a 2 cross 2, 2 cross 2, and 2 cross 2. So the 4 and 4, 8, and 4, 12. So now my size, if I arrange them in a line, they are 12 in numbers, whereas if I try to arrange here, the number is 81. So I have reduced it drastically. This is how the layers can be arranged there. And now we are towards the end of it. So what we can do is, now we put a fully connected. So what we can do, we arrange them in a sequence like this. Okay. So 1.55, 0.551, and likewise. And then I take a simple single layer fully connected network. Okay, so this one is first, then second, and third. So I have, this one is for one image, this one is another image, and now I can use a simple neural network, single layer fully connected neural network to identify it. Okay, and why it identify this X and this as O? Because of some values arrangements there, how they are arranged and how they are placed. Okay, so if I have some value like this, some new image, maybe deformed image, what I can do, I can compare it. I can compare the same image with this. So there is a similarity. How much is the similarity? This is near to this, this is near to this is near, this is near, this is near. So how much similarity is there? That is exactly what neural network will do. It find out that okay, there is a 91% similarity, and then I compare it with 0. Oh, it's a 51% similarity. Which one is having high similarity? Let's say X, so then this image is X. That's all. That's how your CNN whole CNN will understand the things and give us the final recommendations. Okay, I hope you understand these points. So now how many weights we have to train here? So we have to train these weights here. Okay, so these are the weights because it's a fully connected. Also we have to find out a few things which I left here. I think you will raise a question, but if not, then I'll answer it there. Okay, so that's a CNN, and then let's talk about the various models of CNN. Let me check it. Just 1 second. how much time I have. Okay, this we continue till 1:30. Okay. Oh, we have time. We have enough time here. Okay, so then there are the variants basically. Any questions so far if you have? Okay. Let's move to this part, and here is the whole story. So it's not very new area. Started somewhere in 1979 where people tried to work on neurocognition systems, and then ConNet came in 89, and then LeNet came in 1998. But during the after this period, these things jumped in. Okay, so those things you can see early 2000 CNN, and then max pooling appears, and then the ImageNet 2010. Okay, so the first popularity come appear in with AlexNet, that is 2012, and after that you'll find that very fast lot of things will done, like GoogleNet, Inception, V3, V4, V5, ResNet. All these things appear in 2014. They talk about bottlenecks, talk about blocks, talk about parallelism, spatials, and all these things there. 14, then again a breakthrough paper came, that is VGG, which is very popular nowadays. That is in 14. And then ResNet become popular, and you can see that a lot of combinations they came into the picture. All these are seen in models, and now you can see that in last, after the appearance of AlexNet in 2012, in last 12-13 years, this is very popular method which is being used. What is the difference? What they are doing? Let's understand that part. So these are some of the commonly used architecture. I'll talk on this one. LNet 5, LXNet, VGG 16, Inception V1, V3, ResNet 50, exceptions, Inception V4, combination of Inception and ResNet, and then Res next 50. So this is the first one, which is LNet, which came in 1998. Now, I hope if you understood the earlier section, it's now easy to understand it. So there is input layer, and it was initially designed for 32 cross 32 cross 1 image. Okay. And then they have used a convolution layer with the size of 5 cross 5. So 5 cross 5 means the matrix. The filter size is 5 cross 5. Okay. And then they performed average pooling with a window of 2 cross 2. Then again a convolution of 5 cross 5, and then average pooling. And at the end, they have neurons which they arrange into 3 layers, 120, then 84 and 10, and then finally the classification. So it was designed, and what the good feature is basically they have used gradient based learning, and they used for document recognition. Okay, so this architecture has 2 CNN layers. You can see here one and one another layer, and then 3 fully connected layers. So total they have 5 layers. Okay, and this architecture, if you go by the weights parameters, basically it has 60,000 parameters. That was the first one. Okay, so there are 60,000 parameters which are to be tuned there. Then comes LXNet in 2012, which is popular one. You can see the input is image which is which is a colored image, 224 cross 224 cross 3. They've used a convolution layer of 11 cross 11 max pool, then convolution layer of 5 cross 5, then max pool. Then this means 3 convolution layers. Okay, 3 convolution layers, one after another, 3 cross 3, then max pool, then fully connected 4096, another fully connected, and this is the final layer. Okay, So they used for ImageNet classifications, they have used it. And you can see here there are 8 layers, 5 CNN layers, because one here, two, and then three here, 5 layers. And these are the fully connected layers. You can see the parameters, 60 million parameters they have used to train it. Okay, and they have used R means they have used ReLU functions here. So this one is the first one they use the ReLU function. Okay, S means the softmax. Okay. Then comes VGG16. VGG16, they have taken the input same, okay, but they have done it for a large scale image recognition. So you can see the structure size now increases. This two means this set is convolution pool, again convolution pool, then you are here. And then this set is repeated thrice. And then comes the rest of the things. That's why you can see 138 million parameters. Parameter itself take 50 MB of the storage space. Okay, so 138 million parameters, because there are 13 collision layers and 3 fully connected layers. Okay, so they have used more layers, and this is basically deep network starts here. This is twice as deep as LXNet. Okay, so we have stacked them one after another. Stacking features appear there. This they did it for large scale image recognition. Then in 14 again, inception comes in. Okay, and inception came because of the reason. Okay, let's go to this slide. What will happen if you take this pool and then repeat it and repeat it and repeat it? You put so many filters, and because of that, you will see what will happen is the important features die out. So they suggest that if they die out, why not to take the output in between and check it. So you can see output is taken from here, output is taken from here, and then they are evaluating this one separately, this one has this separately, this one has separately, and which one is giving us the best result, they consider it. But what is happening in between? In between the blocks, you can see the blocks are quite big one. You can see. Okay, so they have many blocks there. So this yellow block which is here, it consists of these combinations. The green block is a combination of this one. So now you can see here what they are doing. They are combining the blocks parallelly as well as in a serial manner. Okay. So parallelly means the same data go here, 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 and after processing it, they can create it. Serially means they pass it to one by one. Okay. So this one is basically, you can see now there are 22 layers of architecture, and the parameters are 5 million parameters. They have used some kind of a convolution for dimension reductions. Okay, and this is basically inception. We are taking things from outside and then compare the results and find out which one is the best one. Then comes the inception V3 in 2015, and they used first time batch normalization process. The parameters are 24 million parameters, and basically it is again on inception modulations. You can see more of parallel. Now this one is a combination of parallel blocks, and then parallel blocks, they are connected in series. Again, the inception operation is also there. ResNet 50, very popular one, but you can see now this one is an interesting idea. They use a skip connection. Skip connection means this is skip connection. That the data which is coming, they process through these filters, and then the data as it is also we are taking it and concatenating it. Because what will happen if I use many blocks in serial, the information is lost that I told you. So they go for the residual. So this one is basically, they call it the residuals part, and they connect it. The concept of residual is introduced here. Okay, that is basically ResNet, residual network, and they are designed for 152 layers, 26 million parameters, and they have used the batch processing there. Then comes the exception. It's a combination of the earlier. We have inception modules as well as we have skip connections. So we have combined parameters are 23 million. Well, this is how people keep on developing these things. Then inception version 4 came in. The parameter is 43 million parameters. They have introduced a new module here. And this is how people keep on developing new modules every time. Okay, this one is inception ResNet. So you can see here the upper part is inception part, but there's a complete residual part which is coming at the bottom. The parameters are 56 parameters. They try to understand the impact of residual connections in the learning, and likewise. Okay, ResNet 50 and likewise. So this whole structure keep on moving, and that's why it's important. Like if you have understanding, if you are expert in this domain, then you can work on that how many each block, and then how you connect these blocks, and then you reach to the solution. But if you don't know, that's why then people use NAS here. Okay, NAS, neural architecture search, so that we can get an optimal number of these blocks to maximize our efficiency. That can be another way of doing it. And then people keep on modifying these things because now we know that what is the impact of each block. So then how to put the block and how to arrange the block, that is being a challenge, and still the quest is on. But by doing so, we have a good accuracy, but you see the parameters. We have 25 million parameters or 24 million parameters or something like that. So I'll take one of the figure and then the clear figure. Yeah. So like this figure. Now this one is having 138 million parameter, which is, if you want to train, you can see now you can imagine, if think of like if you have 600 or 1000 X-ray images, and if you want to train it, for every image you have to modify 138 parameters, and you have 1000 images. So how much time it will take? And if you are using a kind of a CPU and all those things, then people have to go for GPUs, and then they also have limitations because the complexity is now big. Complexity, how it is big? 1000 images, 138 million parameters, and say 10,000 iterations. And there comes a new kind of a thought process, and that came because all these Google or Microsoft or other other uh, big industry, what they have done is they have trained these models already, because of they have very high computing facility. Already they have trained it on various parts there. So if I have a model VGG16 which is already trained on X-rays, but not for my problem, so what the suggestion came is, what is happening here in this is the interesting part you need to understand. This part here, this will do most of the time, it will do the job of the feature extraction, and this part which is here, this is doing the part of the classification. So the thought is, if we have already trained model, that means that they are trained to develop a extraction. Only we need to develop this part because of classification for our problem. So the suggestion is that you take the model which is already trained by any of the well-established industry people, that is already available, and then fix these weights. Don't disturb these things. Only update these weights which are very less in number, and then your job is done. If you use this technology, this is known as transfer learning. Transfer learning is nothing but training these weights, outer weights, which are very less as compared to the rest. Because rest is already trained, the feature extraction is already good there. So you just modify it and then do it. So that is how people keep on knowing that how they are using already established approaches and the models and all those things there. Okay. Now let's talk about the case study, and then I'll take your questions before we move to the next session. Okay, so this one is Alzheimer data which is available, and we took this data and we target to make a classification here. Okay, so we have 4 classes you can see here, 1, 2, 3, 4, and otherwise uh, otherwise it's not if you see it, it's difficult. Some pictures you can identify, but otherwise it's difficult. So we want to check it, can we have automated system which can identify these 4 classes. So the pipeline is very simple. We do a little bit of pre-processing because we have to resize everything into 128 cross 128 so that we have proper structuring there. So then we load a pre-trained model. So that is basically we are using a transfer learning kind of structure there. Okay, pre-trained models are already available, and then we replace the topmost layers. That means that is what I have discussed in transfer learning, because of the issue that the computing issue. Otherwise, we need a high computing systems there, and then we train the model and just to check the performance of each. And I think you are now well aware of it. Uh, uh, well aware of all these models like accuracy, precision, recall. These are the parameters on which we evaluated. So we applied ResNet 101, Inception V3, Inception V2, ResNet 50, MobileNet, DenseNet, VG19 and 16. So interestingly, the accuracy of the VGG16 is good with a high precision recall and F1 score. So that make it like kind of confidence that okay, VGG16 is doing good. For our case, for this set of the images, if you change the images, the resolution and all these things, that is always a kind of always a kind of a questions with the researchers in their mind also, like how we do know which one is good and all that. That is still there. Why so? We have to apply some kind of other approaches to figure it out why VGG16 perform better than the rest. But here in this experiment, we checked it. We have these loss curves and accuracy curves and the confusion matrix, which justify that yes, VGG16 is performing better than the rest. Okay, so you can use it. Okay. So the rest are the case studies which we have done it, but I stop it here, and then I'll take your questions. If you have any question, you can put into the chat box or unmute so that we can have a discussion over the things for the next 5 minutes. So if you have any question, next 10 minutes, 5 minutes, I'm there for the questions. So if you have any question, let me know. We can have a discussion so that. Any question, please. You can unmute also. You can write into the chat box also. This is a very interesting domain, very